We're going to talk about beams and shear force and bending moment diagrams. Now, the first thing I'll say is whenever you look at this in a textbook or you're on the internet, you'll always see a shear force and bending moment diagram. They go together. But for some unknown reason, I don't really know why, on the syllabus that we're studying, they don't actually mention shear force diagrams, which is very unusual. They just mention bending moment diagrams. So that's what I'll concentrate on, is the bending moment diagrams, all right? But if you do look at it on the internet or in any textbook, it always has a shear force diagram with it. But anyway, we're just going to focus on the bending moments. We're going to look at simply supported beams. We're going to have point loads initially applied to the beam, and they'll have a reaction points, or RA and RBs, whatever we called them in the previous lecture. And later on we'll have uniformly distributed loads as well. Okay, so in the questions we need to work out what the reactions are and then work out what the bending moments are going to be. It's the next stage in the process. We're going to use the same equation of equilibrium as before. Summation of all the vertical forces equals summation of all the upward forces equals downward forces. And we'll also use the summation of the clockwise and anti-clockwise moments equation. So that's exactly the same equations we've used in previous presentations. Within this presentation, though, there are two different types of beams. We're going to start with looking at the simply supported beam, and then later on we will look at the cantilever beam, and that's where we have a reaction at the wall and a bending moment at the wall, and we have loads applied along the lengths of the beam. A cantilever beam is more like a diving board at a swimming pool, where somebody's sort of jumping off the end, but it's fixed to the sort of foundations at the other end of the beam. So there's a slightly different type of beam, so later on we'll get to those. So this is a typical beam configuration. I said there's sort of the end of the beam there where somebody could be stood on a diving board, that kind of thing, and we're acting the reactions at the wall, moment at the wall, and a vertical reaction at the wall. That's a cantilever beam, a special type of beams. The ones we've looked at so far are the simply supported beams with loads applied in the middle or along the lengths of the beam, and then the two reactions at the end. Okay, so if we go back to what we looked at in a previous presentation, we're going to consider the clockwise, anti-clockwise moments about a point, and I normally take point A as being my position about which will take moments. So don't forget the sort of summation of the anti-clockwise moments, the summation of the clockwise moments. In this case, the anti-clockwise moment would be RD here, multiplied by 5 meters. That would be the anti-clockwise moment, and the clockwise moment would be the 1 kilonewton multiplied by the 1 meter, and the 5 kilonewtons multiplied by 3 meters, and that's shown here. Rearranging, we can find that RD is equal to 3.2 kilonewtons in this case, so we've got our vertical reaction at RD. And then to find RA, we simply add up all the forces, so summation of the upwards forces, summation equals summation of downward forces. What goes up in this case is the RA and the RD, and what comes down would be the, in this case, the 1 and the 5. And again, we can rearrange the equation for RA, knowing what RD is from above. So that kind of stuff we did in the previous presentation. I'm going to skip the shear force diagram, that's what it would look like for the beam, go straight to the bending moment diagram. Okay, that's what we're going to focus on. So we're going to calculate the bending moments. To do this, what we say to ourselves are, what are the bending moments to the left hand or the right hand side of a particular point? I'm going to take bending moments to the left of the points, just to be consistent. So what we say is, if I consider point A and look to the left of point A, if I go back to my original diagram here, top of the page, taking point A, looking to the left of point A, I see nothing. There's nothing to the left of point A. So by definition, there can be no bending moment at A. So that's why MA is equal to 0 by inspection. If I now go to point B of my diagram and I look to the left of point B, what I see now is RA, forces RA, so I've got basically RA multiplied by 1 meter, there's my RA, and it's multiplied by the 1 meter distance in this case, so the moment is RA times 1, RA we said was 2.8, so that's the 2.8 times 1, and that's what's called a positive bending moment in this case, so MB is 2.8 kilonewton meters. We plot that on our diagram, that's a 2.8 there, point B. we go to point C, looking at the moments to the left of point C, then on my diagram, I'm looking at point C here, looking to the left of point C, again I've got my reaction. I can just highlight that here. My reaction still here, the 2.8 kilonewtons. So I've got that now times by 3 meters, because I'm 3 meters away from point C. But now I've also got to consider the 1 kilonewton force, and that's multiplied by a distance of 2 meters from C. 2 meters here. Okay, so on my calculations, the bending moment at C will be 2.8 times 3, that's positive sense. And I subtract now, notice this moment's got a negative sense, the 1 times 2 meters here. And that gives me 6.4 kilonewton meters. With the bending moments, basically what we're saying, a bending moment is that does this to the beam, actually sort of puts the beam into this shape. So a bending moment that's doing that to the beam, we call that a positive bending moment. And a bending moment that does this to the beam, actually makes the beam go in this direction, we call that a negative bending moment. So that's where we get our senses from. So the 2.8 times the 3 is trying to do this to the beam, so it's positive, but the 1 times 2 is trying to do this to the beam, so that's a negative bending moment diagram. Okay, so that's how we get to the 6.4, and then we simply plot the 6.4 at point C on the diagram, there's a point there. And then finally, if we take moments to the left of D on the original beam diagram, so now we'll consider moments about D here, so we're at this point here, then looking to the left, what do I see? The RA again, the 2.8 at the end, I still see that one, looking to the left, but this time it's multiplied by 5 meters it says there, so RA times 5 meters, looking to the left, I've got the 1 kilonewton here, alright, force, but that's now going to be times 4 meters, so that's 4 meters from D, so always from the point you're considering, so 4 meters from there, and I've got now the 5 kilonewton force here, and that's multiplied by 2 meters from D, so that's where the values are coming from, that's 2 meters there. Okay, so in my calculation below, I've got 2.8 multiplied by 5, that's positive, then I subtract 1 kilonewton times 4 meters, then I subtract the 5 kilonewtons by 2 meters. That actually comes to 0, which it should do because bending moments to the right of point D, there's nothing there, so it should be 0. And there's my 0 on my final point on my bending moment diagram. All I do then is just join the points, so my bending moment diagram is as shown there with the straight lines between the points. And that's a bending moment diagram. So the maximum bending moment is actually 6.4 kilonewton meters, and that would be used to design the beam if we were going to take this a stage further. Okay, let's look at some questions very quickly then. So question 1, we're going to work out the shear force and bending moment diagram, so it's just the bending moment diagram we're going to do. We'll go from the beginning here and work out the reactions, but in some of the other questions we'll skip this process, but just for completeness we'll work out the reactions to begin with. So to find reactions, we take moments about a point, so I'm going to use point A. So we say summation of the clockwise moments is equal to summation of the anti-clockwise moments. Doesn't matter which way around you write this, you can have summation of the anti-clockwise is equal to summation of the clockwise, doesn't matter really. So we're going about point A, I've decided to use here, so looking for my clockwise moments in this particular case, I've got 20 multiplied by the distance of 2, there's a 2 meter distance across here, I'll put it in here, that's 2 meters, looking at my geometry, adds up to 8 meters, so 2 meters there, so that will be a 20 multiplied by 2, that's going clockwise, and I've also got clockwise 10, in this case multiplied by 8. Okay, so 20 multiplied by 2 is going in a clockwise direction about A, and also 10 multiplied by 8 is going in a clockwise direction. Anti-clockwise, looking at notation used, that would be RC, and that would be multiplied by, in this case, 5 meters, because I'm 5 meters away from A. There's my 5 meters in here. So that would be 40 plus 80, so 120 on the left hand side is equal to 5 RC. So RC is equal to the 120 divided by 5, and that's 24, and that'll be kilonewtons. Okay, so that's the reaction RC calculated. To find the reaction RA, what we simply do is we add up the upwards and downwards forces. So in this case, if I call that 0.1 there, and 0.2, summation of the upwards forces is equal to, this is the downwards forces. So upwards we would have the RA plus the RC, they're both going up, and then downwards, looking at the diagram above, we would have 20 and 10, so 20 plus 10. We already know that our C is equal to 24, so it would be 30 take away 24, and I rearrange my equation, so RA is equal to 6 kilonewtons. So now I've got my values for the RA and the RC in this case, but I can write them in now. So RC here is equal to the 24 kilonewtons, and the RA is equal to 6 kilonewtons. Okay, what we've got to do now is work out the bending moments at the various points along the beam. So calculate bending moments. So we're going to take moments to the left of the various points, so take moments to the left hand side of each of the points. So the bending moment at A, call it MA. So looking to the left of A, there's nothing to the left of A, so we sometimes put by inspection, by looking, nothing to the left of A, so that's the point A done. So now we're going to look at the left of B. Looking to the left of B, what do I see in terms of my force times distances? Don't forget it's moments we're looking at. And I see the RA, which is 6, and that's multiplied by a distance of 2. I'll 2 back in here, there's 2 across here. RA times 2, so 6 times 2. In this case, that will be 12 kilonewton meters. If I now move my position to the left of C, looking to the left of C, what do I see? Well, I've still got the 6 kilonewtons for the RA, but this time it's multiplied by 5 meters from C, and I see the 20 kilonewtons multiplied by 3, but that's negative, the negative bending moment, so that's 20 multiplied by, in this case, 3. So looking at the numbers on that, 6 times 5 is 30, take away 20 times 3, which is 60, so negative 30 kilonewton meters. And then if I look to the left of D, and there should be 0, but just to check it out, I should be seeing 6 multiplied by the 8 now, so the RA is 8 meters from D. Let's label my D here. Look at this point here, so it's 8 meters from D, the RA location. The 20 kilonewtons is negative the 20, now that's going to be 6 meters from D, so that's multiplied by 6 now. And I also see, looking to the left of D, RC, which is 24, and that will be a positive 24, because that's given a positive bending moment, and that's multiplied by 3 meters. We'll do the calculations on that. That will be 48 minus 120 plus that's 60, 72. So hopefully we're seeing 72, 80, yeah, that's equal to 0. And of course it should be, because bending moments to the right of D, there's nothing there, so it should be 0. So it's like a little check for ourselves. That allows us now to draw the bending moment diagram. I'll do that at the top of the page for convenience. So if I label my axis, so this is point A, this is point B, point C somewhere up here, and point D. They should be drawn more or less to some kind of scale. Okay, we know the bending moment at A is going to be 0. The bending moment at B, according to our calculation, is going to be 12, so I'll draw that sort of there. The bending moment at C is negative 30, so to sort of scale that will be down somewhere here, and the bending moment at D is 0. So the bending moment diagram, we draw these, we'll plot these points with nice straight lines between each of the points here. Okay, and sometimes you see the diagrams are shaded. If you look in a textbook, they're often shaded in. So we should label the diagram. This is a bending moment diagram. We should always put the units after it. The units are kilonewton meters. And if you want to be really clever, you can put the sign convention in. You wouldn't be expected to really put this in, but the sign convention would be of this kind of shape, where you've got the bending moments like that. It looks like a smiley face, really. It's an arrow, and that's the positive bending moment notation. Okay, that's for completeness. But it's a diagram you're really interested in labeling the diagram. So there should be nice straight lines between the points there. And that's a bit curved, my lines, but they should be straight. And that's it. That's the bending moment calculations done. Let's get this one, question 2. In question 2, we've got some masses here. Sometimes you get this kind of problem. So what I think I'll do first of all is rewrite my beam, but I'll calculate the actual forces here. So this is my beam, and I've got the RA on the left hand end. I've got RD, they've called it, RD on the right hand end here, so using their notation. So we've got to find RA and RD, and what they've done is given us these masses, there's like hanging masses from the beam in these locations here. So we need to work out what the masses are going to be. So I'll do that up here, I think. So if I call this W1, so I want to work out the masses in terms of forces. So W1, we're given 3 tons. Don't forget, as it says in the question there, that 1 ton is equivalent to 1,000 kilograms. So that will be a mass of 3,000. And don't forget to convert it into a weight force. We multiply by 9.81. That's going to be, my calculation is 29.43 kilonewtons. You can work in kilonewtons or newtons, whatever you prefer to work in. And then W2, very similar. That's just 1,000 kilograms times the 9.81. So that's easy. That's 9.81 kilonewtons. You want to work in newtons, and that's fine. In kilonewtons here. Okay, so now we've got our forces, so I can replace the W1 and the W2 with those actual values, make it easy to follow. So this is my 29.43 kilonewtons. This is my 9.81 kilonewtons. We're going to find the reactions very quickly. So we need some dimensions here. We know this is going to be 1.2 meters, given information above. We'll be taking moments about RA, so I need all the geometry, all the dimensions about A. So that one now will be 3.2 meters. And of course we know the length of the beam between the reactions in this case is going to be 4 meters. Okay, so we're going to work out the reactions. So to find reactions, so take moments about point A. So the summation of the clockwise moments equals summation of the anti-clockwise moments. So looking at my moments about A, clockwise, I would get 29.43 multiplied by 1.2 meters, and I add to that my 9.81 here plus 9.81, that's multiplied by 3.2 meters, and that's equal to the anti-clockwise moments. That would be RD, and that's multiplied by 4 meters in this case. Okay, evaluating that, I think that works out to be 66.708 I'll let you do the arithmetic there, is equal to 4RD. So rearranging, RD is equal to 16.67. Okay, I'll just put it into decimals there. They've got 16 2/3 on the sheet. And then to find RA, we summate vertical forces. So that was step 1. Step 2, make vertical forces. So the upwards forces equals to the summation of downward forces. So up in this case we'll have RA plus RD, and downwards we will have 29.43 plus the 9.81. We already know RD anyway, so RA will equal to 22.563, and that'll be in kilonewtons here. We'll check that out. So we've got our reactions now. Okay, so now we've got our reactions. I need to work out the bending moments. Okay, pull the beam again just for convenience. So this time I know my RA is going to be 22.563 and my RD is going to be 16.67 kilonewtons, and I've got my 29.43 and I've got my 9.81. Okay, so we're going to calculate the bending moments now. Take the moments to the left hand side, just doing that for consistency. So by inspection, MA will equal to 0. If we take moments to the left of the point A here, there's nothing to the left of A, so I've got the 0 by inspection, and force times distances as such. If I now take moments to the left of B, so I should label my A, B's and C's for convenience. This is A, this is B, C and D. So taking moments to the left of point B, I've got my distance of 1.2 meters there. So I will have 22.563 multiplied by 1.2 in this case. That's a positive bending moment, and that gives me 27.076 or 08, and that's kilonewton meters. That's bending moments to the left of the point B there in that case. I go to the left of point C here in this particular case, and looking at my geometry, that's going to be 3.2 from above. I also need this distance in here now, and that's going to be 2 meters. Okay, so my bending moment now to the left of point C, I will get the 22.563 multiplied by 3.2. I take away from that the 29.43, and that's multiplied by 2 meters in this case. Evaluate that. 13 1/3. If you want to check that figure out, 13.3 recurring. And again, it's kilonewton meters is the unit we're using there. Just to show slightly different, take bending moments to right hand side, then I can say that the M at D is equal to 0 by inspection, and that's what an engineer would actually do. They wouldn't really calculate the bending moments to the left of point D, they would just say to the right, you can see it's 0. So now I can plot my bending moment diagram. It's like the 0, 0 line here. This is point A on my beam, point B on my beam, point C, point D. And all I do with the bending moment diagram is literally plot the points. I just plot the coordinates. So we know bending moment at A over here, this bending moment here is 0, so that'll be 0 on the diagram. Bending moment at B, on our calculations here, it's 27.08, so 27 nominally. We just plot that on the diagram. So at B, we will now simply put a cross. It should be to scale, really, some kind of scale, sort of up at sort of like 30 almost, isn't it? There, that would be the 27.08 value. Okay, all I do is draw a line, a linear line between those 2 points. that was point B dealt with. At point C, the bending moment is given as 13.3 kilonewton meters. So on my diagram here, sort of scale would be somewhere down here. That would be sort of 13ish scale, and that would be at point C. And I would just draw a line between those 2 points, a linear line between those 2 points. So I see there, and at point D, so here, then the bending moment at D is going to be 0 by inspection. So I just simply draw my line, linear line again from there to D. Alright, so we're literally plotting the points on the bending moment diagram. Usually they're shaded in. Alright, so that point there would be my 13.3 kilonewton meters. Okay, so that's my bending moment diagram. And kilonewton meters, put the unit down, and if you want to be really clever, you put the bending moment rotation down. And that's job done again. Okay, so that solved our question 2. Question 3. It's actually a symmetrical beam here. Now, an engineer likes symmetry because symmetry helps them with the analysis. Because the beam is symmetrically positioned, so the supports, the RB and the RD, the reactions are symmetrical, and the loading is symmetrical here when we look at it, we can actually write down by inspection the reactions. We don't need to do any calculations really here. No taking moments about A and summating vertical forces. We could make a note here, and it's useful to know this because engineers do like symmetry when it occurs. If we put a note, as the beam is symmetrical in geometry and loading, the loading applied is symmetrical as well, then the RB must equal to the RD. They must be exactly the same, and they're basically going to be half the applied loading. So in this case, RB will equal to 20 plus 70 plus 20, all divided by 2. So adding them, that's 110 divided by 2. So RB is equal to 55 kilonewtons, and by symmetry that's the same as RD. Alright, so because it's symmetrical, that's the key. It's a symmetrically loaded beam, and geometry is symmetrical, loading symmetrical. You can straight away write down the reactions. So this is 55 kilonewtons, this is 55 kilonewtons. None of the other beams we've had so far have had that characteristic. They've always been unsymmetrically loaded. So that actually makes the bending moments easy to do as well, because you only need to work out the bending moments at B and C, and you've got the bending moments for the entire beam here. So it's a quicker problem once you see it's symmetrical. We're going to work out now the bending moments. So find the bending moments. We're going to take moments to the left hand side of each of the points we're going to consider. So we'll take moments to the left hand side of each. So by inspection, we take moments to the left of point A. Point A there's nothing to the left of point A, so the bending moment will be 0. We'll put by inspection. We now consider point B here, and looking to bend moments to the left of point B. Now we'll see negative 20, be careful, it's negative 20 kilonewtons multiplied by 1. It's negative because of the effect the bending moment's having on the beam. It's what's called hogging the beam. So it's a negative 20 times 1 in this particular case, so negative 20 kilonewton meters. And if we take bending moments to the left of point C, we will see that the bending moment at C is going to be negative 20 multiplied by 2.3 now, or 2.3 meters away from C. And then we're going to add the reaction, 55 kilonewtons multiplied by 1.3, so multiplied by 1.3 equals 2. That gives me a value from bending at C of 25.5 kilonewton meters. Now by symmetry we can see that the MD is equal to the MB, and of course the ME is equal to the MA, equal to 0. So we've got all the points we need to plot our bending moment diagram, so we can do that now. So over here, put my beam, and as always we should title the diagram. This is a bending moment diagram, units, kilonewton meters, and again if we want to put the positive notation down for the bending moments. And there's the solution to that question with the bending moment diagram. And question 4, we're just given a practical context here really. So we've got this shaft with the pulley located along the shaft. So the pulley is where we have these loads. These are actually tension in the belt that's wrapped around the pulley, and it's being reacted at the bearings here on the right hand side. So the idealization here is that we've got a simply supported beam effectively. There's a beam across there. We've got the point load in the middle, and we've got the reactions at the end here in here. So that's the idealization of the beam. Okay, so that's sort of the art, if you like, of the engineering approach here. We're given in the question that the total tension T1 plus T2 is 1750 newtons. That's given in the question. So basically we've got a simply supported beam with a load in the middle. The directions of the loads, or direction of the arrows here, are slightly unusual. We normally find the arrow above the beam going down and the reactions going up, but in this particular case with the scenario, then the load in the sort of central load in the beam is going up, so the reactions must go down. So as usual, the first thing we're going to do is calculate the reactions of the beam. So we're going to take moments about a point, and I suggest as always we take moments about point A to find the reactions. So find reactions, they've called them RA and RC. Summation of the clockwise moments equals the summation of the anti-clockwise moments. So about the left hand end, clockwise moments would be RC this time multiplied by 0.8 meters, looking at the beam. So there's my RC. Okay, that's force RC, and we multiply it by the distance we are away from RA, so that distance is 0.8 here. And that's a clockwise sense, that's going in this sense about the point A, so it's a clockwise sense. An anti-clockwise sense, this time we have the central load here, this 1750 newtons, and that's 0.5 meters from the point A we're considering, and of course that's an anti-clockwise sense there. So on the right hand side of the equation, 1750 multiplied by 0.5 meters in this case. So simply rearrange the equation now. So RC is going to equal to 875 divided by the 0.8, and that gives us approximately 1094, and this time it's newtons we're using here. To find the RA, we simply summate vertical forces. So that was basically step 1, using the moment equation. Now we're going to use the upwards downwards forces equation. So summation of the upwards forces equals to summation of the downwards forces. So upwards we've got 1750 newtons, and downwards we've got the RA plus the RC. We want to find RA, so rearranging, the RA will equal to the 1750, and then take away the RC from above, the 1094. So therefore the reaction RA is equal to, in this particular case, 656. There's our reactions. Now we need to work out the bending moments. So to work out the bending moments, we need to take moments to the left of the various points on the beams. So to calculate bending moments, I'm going to take moments to the left hand side of the various points we'll consider. So we're going to consider the first point is A. So looking to the left of A, then the bending moment at A is 0, and put by inspection. The bending moment at B is equal to, then we've got the negative RA, RA in this case is 656, so it's negative 656 multiplied by the 0.5. So that gives a value of negative, in this case, 328 Newton meters. Finally, my bending moment to the left of C, that would be negative 656, this time multiplied by the full length of the beam, which is 0.8. And I would add to this the 1750, and that's 0.3 meters away from C. That evaluates to give me 0, which of course it should do. The bending moments to the right of C would be 0. So I'm now in a position where I can actually plot my bending moment diagram, taking this as my 0 position. Then we know the bending moment at A is 0, the bending moment at C is 0, but the bending moment at B is negative 328, so I'll draw it down there. And don't forget, as always, we put nice linear lines through these points here, linear lines here. So that's negative 328 Newton meters. Okay, we sometimes shade in the bending moment diagrams. So my bending moment diagram, the units are Newton meters, and again, if we want the positive notation, we can show this little diagram here. So obviously we've got a negative bending moments here, so it's going against this notation. But that's the bending moment diagram drawn for us there. So more of a practical orientated problem there, a shaft in a pulley situation, showing how it's idealised, and then showing how we go about working out the reactions and, in this case, the bending moments. Once we know the maximum bending moment, we can actually then design the beam, or the shaft in this case, taking the analysis a bit further. But for this presentation, we'll stop there. I will leave you with 2 further questions to attempt at your own pace. Question 5, simply supported beam shown here. You've got to calculate the reactions RA and RE, shown here, and also construct the bending moment diagram. Answers are shown in the bracket. And finally, question 6. Again, you've got to calculate the reactions. This time it's RB and RE, shown here and here, and then construct the bending moment diagram. Again, the answers are shown in the bracket. So I'd encourage you to stop the presentation and attempt these questions to try and consolidate your learning related to drawing bending moment diagrams where we have point loads applied to simply supported beams.